Welcome back to Manish Kumar channel. Today we are interested to discuss about limit of complex functions. So what is the limit of complex functions? Let f be a function defined on all points in some deleted neighborhood of z naught, right? The statement limit z tends to z naught fz equal to w naught, right? We will denote it as equation number 1. In more precise way, we can define or we can say that epsilon delta definition, right? So for every epsilon greater than 0, there exists a delta greater than 0 such that mod of fz minus w naught is less than epsilon whenever modulus of z minus z naught is less than delta and greater than 0, right? So in geometric terms, for any neighborhood of W naught of radius epsilon, right? That means the set W such that W minus W naught modulus is less than epsilon. There is a corresponding deleted neighborhood, right? Of Z naught of radius delta. That means the set Z such that modulus of Z minus Z naught is less than delta and greater than 0, right? Such that every z in that neighborhood is mapped by f into the epsilon neighborhood of w naught. So if you see, this is your z plane and this is your w plane, right? And you have your function f from z plane to w plane defined by fc equal to w, right? Then any delta neighborhood for every epsilon greater than 0, so you will get a center w naught and then you will get a radius epsilon disk, and any w and w naught, this distance is less than epsilon, so w minus w naught is less than epsilon whenever you will find z minus z naught is less than delta. So we are interested to find some delta, right? There exists a delta greater than 0. If we are able to find a delta greater than 0 which works for every epsilon greater than 0, then we can say that limit exists, right? So note that even though all points in the deleted neighborhood, right, are to be considered, their image need not fill up the entire neighborhood, right? If you see, if we define my function as some constant, let's say w naught, fc equal to w naught, which is a constant, right? So what had happened is whenever I move in any arbitrary delta neighborhood, then always I will be reaching to a fixed point w naught, right? So it need not fill the entire this epsilon neighborhood. Okay. So now here is if f has the constant value w naught, for instance, the image is always the center of that neighborhood, right? Okay. So once we found a delta, it can be replaced by any smaller positive number, such as delta by 2, delta by 3, delta by 20, and so on, or delta by 2005, right? What does it mean? It means that delta is not unique, right? In fact, there are infinitely many possible values of delta that satisfy the given condition epsilon, right? So now it emphasizes that many values of delta may work for a given epsilon, not just one, right? And this we will see in the next video, right? Now let us see the uniqueness of limits. So this is similar to your linear algebra limit. Here we are talking about, complex plane. So if the limit z tends to z naught fz exists, then it is always unique. And proof is very simple. You can assume there are two limits, let's say w1, w2, such that limit fz tends to z naught equal to w1 and limit z tends to z naught fz equal to w2. It means that let epsilon greater than 0, since this is the limit w1, then I can always find a delta. There exists a delta 1 which is greater than 0, such that mod of z minus z naught is less than delta 1 and greater than 0, implies fc minus w1 is less than epsilon by 2, right? Similarly, it will also give you this equation, right? fc minus w2 modulus is less than epsilon by 2. Now we are going to choose the minimum of delta 1 and delta 2, right? Minimum of delta 1, delta 2. That works for both basically, right? So if I replace this delta 1 by delta and this delta 2 by delta, then the result still holds true. Okay. Then for any z such that this condition holds for delta, we can write w1 minus w2, which is equal to, I'm going to add fz and subtract fz, and then using triangular inequality, right? We can write it in two parts, and then which is nothing but epsilon, right? It means that since epsilon greater than 0 is arbitrary, it follows that w1 minus w2 is equal to 0. Because if you see here, this will work for every epsilon. Right hand side will work for every epsilon. So what will be the possible modulus value? The possible modulus value is 0. For example, if you say epsilon is half, right? Epsilon is half. So modulus of w1 minus w2 is going to be, let's say someone says w1 minus w2 is 1 by 4, right? So this means this difference w1 minus w2 is going to be 1 by 4. This difference is 1 by 4, means 1 by 4, which is less than half, right? But since epsilon is arbitrary, so someone comes in and then say that no, I want epsilon is 1 by 5, right? Then your this result may not hold true, because 1 by 4 is not less than 1 by 5, right? So this result is not valid. So what you have to do is you have to revise your this value 1 by 4. So you assume 1 by, let's say, 7. So 1 by 7 is less than 1 by 5. Then somebody comes into the picture and say that no, I want to take epsilon as 1 by 1000, right? So what is the possible value of this fellow? So this fellow should only be 0, then which works for all epsilon. That is what since epsilon is arbitrary, so it follows that this difference modulus is going to be only 0, which implies that w1 minus w2 equal to 0, which implies w1 equal to w2. Hence the limit is unique, right? This is a very important result. Now more theorems on limits. So if you see here, the theorem 1, suppose fz can be written as u plus iv, and z naught is defined and w naught is defined like x naught plus iy naught, w naught equal to u naught plus iv naught. Then limit z tends to z naught fz equal to w naught if and only if the real part limit and imaginary part limit exist as u naught and v naught, right? Similarly, the next theorem, if limit z tends to z naught fz equal to w naught and limit z tends to z naught z of z equal to w1, two functions, right? Then what about their sum? Sum of uh, the function and then taking limit is equal to limit of individual sum, right? Then what about their product? And similarly, what about their ratio, provided W1 is non-zero, because otherwise this factor is not defined, right? So this is algebra on limit, we can say. So these are the important property. Now extension of limit definition to boundary points, right? So definition 2, that is epsilon delta definition, requires the function f to be defined for all points in some deleted neighborhood of z naught, right? So such a neighborhood always exists when z naught is an interior point of the region, right, on which f is defined. To extend the definition of a limit to the case where z naught is the boundary point. Boundary point means if you have circle and this is the boundary point. So whenever you prepare a neighborhood, what had happened? Some points are going outside of the set and some points are inside the set. So here the question is, we will consider the neighborhood, all those z which are common to the region as well as the neighborhood. So this is your neighborhood. So we are going to take this point only. This is the how we are going to define the neighborhood, right? So to extend the definition of a limit to a case when z naught is a boundary point of the domain, or you can say region, right? We agree that the condition 2 needs to be satisfied only by those points that belongs to the both region of f and the deleted neighborhood of z naught. So this is the common point they are talking about. If you take any point here, prepare a neighborhood, right? Then you have to take the common point of your region. This region you have to take any z, right? Okay, and this we will see in example 1. Okay, so now let us see example 1. So that if limit fz equal to I z bar by 3 in the open disk modulus z is less than 1, then limit z tends to 1 fz equal to I by 3. The point 1 being on the boundary of the domain of the definition of f. Observe that when z is in the disk modulus z less than 1, so what is the definition? Fc minus w naught. So this is actually w naught, right? So which we are going to plug the function value and then we are going to solve it, z minus 1 divided by 3. Hence for any such z, each positive number epsilon, we can see in figure 2, fc minus I by 3 is less than epsilon whenever 0 is less than z minus 1 modulus less than 3 epsilon, right? So condition 2 satisfied by points in the region modulus z less than 1 when delta equals to 3 epsilon or any smaller positive number work, right? So if you see the picture, this is your region inside given open disk, right? And then you can perform limit z tends to 1, right? This is the limit we are talking about of the given fz. So now when you reach towards this will become almost on the boundary, right? And then in that case, whenever you prepare a neighborhood, then what had happened, some portion, the gray portion is going to be considered only, right? This part is no longer in the domain. And in that case, you can always define a function f from this to this, and then you will get I by 3 smaller neighborhood, and this is the elaboration of your picture, right? If the limit 1 exists, then notation z tends to z naught signifies that z can approach to z naught in any manner, not just along a specific direction. You can reach to this point in this neighborhood by any path, right? Or you can move by any straight line over x-axis, or any path you are going to move towards the z, right? You can move toward any z can be moving toward this by any path, any parabolic path or any straight line or any direction you have to move. That is what this meaning is, right? So thank you very much. Thanks a lot.